In this video, we are going to study upper and lower limits, which are more popularly known as lim-sup and lim-inf. They are very useful in the study of sequences that are actually not convergent. So the definition is quite straightforward. Definition: let xn in R be a sequence. Define S, which is actually a subset of R union minus infinity, the extended real numbers with the points minus infinity and infinity added. I remind you again that these are not real points, they are just a notation. To be set of all x in R union minus infinity such that there is subsequence x and k that converges to x, or rather it could converge to x if it's a real number, or it diverges if you want the point infinity to be in this set S. There should be a subsequence that diverges to plus infinity. Similarly, if you want minus infinity to be there in this set, you need a sequence x and subsequence x and k that diverges to minus infinity. Now the lim-sup of xn and going to infinity is just by definition supremum of the set S. If this set S is unbounded, or if the set S contains the point plus infinity, the supremum is taken to be plus infinity. Similarly, lim-inf xn and going to infinity is just the infimum of the set S with the same remarks. If the set S is either not bounded below or it contains the point minus infinity, then the lim-inf is just minus infinity. So immediately you can characterize this lim-sup and lim-inf in several ways. I'm going to leave one exercise for you. Show that lim-sup and going to infinity xn is just equal to limit n going to infinity supremum, or rather limit this is correct, limit n going to infinity supremum of xn plus 1 comma dot dot dot. You just start taking the supremums of the tails and then take limit n going to infinity. So there's one just this one remark that needs to be made. This could be plus infinity. Okay, so you will have to be a bit careful when you analyze and prove this exercise. You will be taking limits where some of the terms could be infinity. So I want you to handle this with a bit of delicateness. It's not that difficult, but let me just tell you that this could be plus infinity, and not only that, if it's going to be plus infinity for some n, it's going to be plus infinity throughout. That will give you the key. So it's just going to be a constant plus infinity. It cannot happen that supremum xn plus 1 is plus infinity, but when you remove finitely many terms, suddenly the supremum becomes finite. That's not going to happen. Okay, similarly lim-inf n going to infinity of xn is just limit n going to infinity of infimum of xn plus 1 and so on. Okay, so these are the basic properties of this is one of the basic properties of lim-inf and lim-sup. You can characterize it in terms of both subsequential limits as well as this definition. Now about characteristic properties, there is a very good characteristic property of lim-sup and lim-inf that you must know. And this formulation is what is used in proofs most often. Theorem: let xn be a sequence, then lim-sup n going to infinity of xn has the following two properties. Property number 1, there exists a subsequence x and k such that x and k, if you don't mind, let me just call this lim sup s upper star. This is a common notation. X and k converging to s upper star. Okay. Property number 2, if x is greater than s upper star, if you choose a real number that is greater than s upper star, there exists n such that if n is greater than n, then xn is less than x. Okay. So in some sense, the lim sup is not an upper bound for the sequence, it is an essential upper bound. After a particular point, you cannot become greater than, you cannot become greater than any number greater than the lim sup. Okay, that's a mouthful, but it is a very, very intuitive property. The sequence will not be too far greater than lim sup, provided you go far enough in the sequence. So let's prove this characterization. Proof. Suppose s upper star is plus infinity. Okay, then the only way by which this can happen is then xn is unbounded. It's an unbounded sequence. It is easy to find x and k diverging to plus infinity, and I'm going to leave it to you. Okay. Now suppose xn is bounded. Xn is a bounded sequence, then clearly s star is a real number, obviously. Okay. Now this means there must be at least one convergent subsequence. This is just the Bolzano-Weierstrass theorem. Convergent subsequence. Any bounded sequence must have a convergent subsequence. Okay. So this set S is non-empty. Non-empty is a non-empty set of real numbers. Okay. And we already know that given any non-empty set of real numbers, we can always find a point, a sequence, let's say, not just a point. We can always find a sequence. We can always find a sequence in S that converges to supremum of S. Oh, I must mention this set S is the same that we saw in the definition of lim sup. I have defined a set S. I am going to reuse the notation. Okay. Now what I am trying to say is that given this set S is a non-empty and bounded set, we can always find a sequence in S that converges to supremum of S. This is always true. Now for each point in this sequence, so let's just call this sequence yn. Okay, let's just call this sequence yn. For each point in yn, there is some subsequence that converges of xn that converges to yn. Okay. Now it is easy. The very similar arguments we have done several times before. It is easy to construct a subsequence of xn k of xn that converges to supremum of S. This is something that we have done several times earlier, some very similar arguments, so I'm going to leave the rest to you. Okay. So there is a third possibility that we should consider. What if this set of subsequential limits, that's a empty set? Okay, not an empty set, it consists of only minus infinity. That's possible. Suppose S star is minus infinity. What if the lim sup itself is minus infinity? Okay, this just means there is no subsequential limit. There is no subsequential limit whatsoever. Limit at all. Okay, that just means for given any real number, m, given any real number m, xn is greater than m only for a finite number of values. Of n. Why is this the case? Well, think about it this way. If it's not true that xn is greater than m only for a finitely many values of n, then that just means that there is a subsequence of xn that's strictly greater than n. Now there are two possibilities. This subsequence could be bounded, in which case we can apply the Bolzano-Weierstrass theorem to get a further subsequence that converges, contradicting the fact that there is no subsequential limit at all. On the other hand, if this xn is unbounded, then you would get a subsequence that diverges to plus infinity, again contradicting the fact that there is no subsequential limit whatsoever. Okay, so what this shows is that only finitely many values of n are for only finitely many values of n, xn is greater than m. It is easy to now construct a subsequence diverging to minus infinity. Okay, so this will provide for you the subsequence that diverges to minus infinity. Now on to the second part. Let's just recall. The second part asks us to show that if a number is greater than S star, then there exists n such that if n is greater than n, then xn is less than x. Okay, now again we can use a similar logic to what we have seen so far. Do the following. Suppose this S star is a real number. It's a real number. Of course, if S star is plus infinity, there is really nothing to show. Okay, so suppose S star is a real number and x is greater than S star. Okay, then if xn is greater than x for infinitely many values, infinitely many n, then there is a subsequence. Again, same logic, there is a subsequence xn k which is strictly greater than x for all k, right? Now there are two possibilities. If xn k is unbounded, then in fact S star is plus infinity, which is nonsense. On the other hand, if xn k is bounded, the Bolzano-Weierstrass theorem guarantees, or let me just say gives a subsequence of xn k that that converges to a point greater than or equal to x, which is, again, this is not possible because x is the supremum of all subsequential limits. Okay, now the case where x is just s star is just minus infinity is very easy. If s star is minus infinity, it's rather trivial to show this. Okay, now this actually concludes the proof of property 1 and 2. I just want to make a remark, or rather I'll give an exercise. Show that 1 and 2 characterize lim sup uniquely. That means if there is a number that satisfies 1 and 2, then that has got to be the lim sup. Okay, so I'm going to leave further exercises in the lecture notes where you extend the root test and the ratio test, make it slightly stronger, incorporating our knowledge of lim sup and lim inf, and I'm also going to leave the Cartan-Hadamard theorem for the radius of convergence of a power series, which is just a straightforward application of the root test, to you. You will be able to compute a formula for the radius of convergence of a power series. There are some more examples also of these notions in the lecture notes. This is a course on real analysis, and you have just watched the video on upper and lower limits.